Hello all, in this video we are going to see about geometric parameters of 3D points, plane, line and quadrants. So in previous video we have seen 2D points, 2D lines and 2D conics. Here the same can be represented using 3D. Okay, first let us see 3D points. Usually we'll represent a point in 3D as x comma y comma z. This point can be represented in real space, or we can say it as Euclidean space. Okay, or we can say it is a real space represented by R. Since it is 3D, I'm representing as R per 3, which is nothing but an ordinary 3D point, right? So, which is an ordinary 3D point. Uh, it is an inhomogeneous coordinate or inhomogeneous point. Okay, in order to represent the point in a computer graphics or computer vision, we have to represent it as a homogeneous point. Okay, we can represent the same as, so let us write x equal to x comma y comma z. We can represent this in homogeneous space using additional point w bar. This is nothing but projective space. This is a projective space. This represents homogeneous point. This represents the homogeneous point. Okay, so we know how to represent inhomogeneous point and we know how to represent homogeneous point. Okay, so for example, we need to convert inhomogeneous to homogeneous or homogeneous to inhomogeneous. So inhomogeneous to homogeneous means x comma y comma z has to be converted to x comma y comma z with additional parameter. Let us consider it as 1. Okay, if we want to convert it to inhomogeneous again means we can divide it by 1. Homogeneous to inhomogeneous, so homogeneous x comma y comma z comma 1. If we divide this 1 with all the three parameters x comma y comma z, right? So this inhomogeneous will be converted into homogeneous. So in general form we can write, okay, in general form we can write what we have written in general form: inhomogeneous x bar y bar z bar w bar, right? We can write it as x bar comma y bar, sorry, x bar divided by w bar, y bar divided by w bar, z bar divided by w bar. If this w bar is 0 means the denominator will become 0, so we can say it is the point at infinity. So general form is x bar comma y bar comma z bar comma w bar. We can represent it as x comma y comma z comma 1. So how we are equating this? The 3D point can be represented as x bar into w bar, which means we know that x bar is x comma y comma z comma 1 into w bar. So we are writing x w bar into x, w bar into y, w bar into z into w bar. Okay, this w bar and x are represented as general term of x bar. Okay, so x bar comma y bar comma z bar comma w bar. Okay, so we can say x bar is nothing but w bar into x, y bar equal to w bar into y, z bar equal to w bar into z. This w bar x, w bar y, w bar z is represented as x bar, y bar, z bar. So this is the general way of representation. This is the explicit way of representation. Okay, so that's what given in the previous slide. X equal to x comma y comma z or the ordinary inhomogeneous candidate representing in real space. We can convert it to the homogeneous coordinates as x bar equal to x bar, y bar, z bar, w bar. So which is the one I have represented here. Okay, so which is the projective space. We can represent the 3D point using augmented vector as x comma y comma z comma 1. So this 1 is nothing but the w bar. Okay, so on dividing this we are getting x bar, y bar, z bar. So the general point representation is x bar equal to w bar into x bar, right? So this is the general way of representing 3D points. Next, 3D planes. 3D planes, this is the 3D plane representation. We are having three coordinates x, y, z, and we are drawing a plane on it, and the plane is named as M. And this N is the perpendicular direction, okay, and D represents the direction. Okay, perpendicular distance represents the n bar, and D is the direction. Right. So the general equation is x bar into m bar equal to ax plus by plus cz plus d equal to 0. We know that general plane equation is m bar equal to a b c d, and the point is represented as x comma y comma z comma 1, right? So m into x represent ax by c z and plus d equal to the dot product of point and plane equation. Okay, this point we know how to represent in the previous slides, and we are normalizing it with the n as 1. So we are representing n cap x, n cap y, n cap z, and d equal and d. Okay, so in general we are representing all the three terms as general n bar and d, where n is the normal vector perpendicular to the plane and d is the distance from the origin. Okay, d is the distance to the origin. As we said earlier, m bar equal to 0 comma 0 comma 1 means we are saying the plane is at infinity. Like in previous case we have said, right? So if w bar equal to 0 means the point is at infinity. Similarly, for this equation, if a is 0, b is 0, c is 0, and d is 1 means then we can say the point is at infinity. Okay, so if we are going to represent the spherical coordinates, which means represented using cos theta sin theta, then we can say the n cap as cos theta cos psi, sin theta cos psi, and sin psi. This is the spherical representation using the two angles theta and psi instead of polar coordinates. Okay, this is the polar coordinates. Instead of theta, we are representing A, B, C, D, right? This is the polar coordinates. If you are representing angle means, then it is a spherical coordinate. Next, we are going to see about lines. The 3D plane is represented here, X, Y, and Z, right? X, Y, and Z. A line is drawn. When we draw a line, we will have 2 points, right? P and Q. Assume that we are having a 2 points P and Q, and if we want to determine any of the point like R lies in the plane or not, we can use this equation. Okay, so we are having 2 points P and Q. Any other point on the line can be expressed as a linear combination of these two equation, which means if lambda equal to 0 means, this part would become 0. 1 minus 0 into P plus 0 into Q, which is nothing but P. The R is nothing but P. In case if lambda is 1, then 1 minus 1 into p plus 1 into q, this is 0p plus q. If lambda is 1, we can say q is nothing but r. If any point, like if the lambda value is between 0 to 1, then we can say the point r lies between this p and q. If the lambda is greater than 0 or greater than 1, which means lambda is less than 0 and greater than 1 means we can say the point r is not in the line, which is out of the line. So in this way, we can represent a 3D line and we can determine any of the points lying between the 3D line or not, right? So the normal 3D point, we know that it is x comma y comma z. It is general, a normal 3D point. So which is inhomogeneous, right? Which is inhomogeneous. If you want to convert to homogeneous, then we can write x comma y comma z comma w, which is homogeneous. Why we need to convert into 4? We are additioning 4 parameter, right? So if we want to write any or draw any shapes in infinity, the infinity point can be used in computer graphics or computer vision. So in order to represent the point in infinity, we are adding this fourth parameter. If we want to represent the point in infinity, we can add a 0 here. If not, we can add any other values. So in this case, if you want to represent the fourth parameter, we have to use this equation is for inhomogeneous. This equation is for homogeneous. We are going to use mu p bar. Note the difference. In homogeneous, we won't represent any bar. In case of homogeneous, we are converting it p bar plus lambda into q bar, where this mu is nothing but x bar, y bar, z bar, and w bar. Okay. In homogeneous, we are writing 1 minus lambda to represent x comma y comma z. In case of homogeneous, we are writing mu to represent x bar, y bar, z bar, and w bar. So a special case of this, when the second point is at infinity, that is q bar. Like if the second point, first point is p, second point is q, if the second point is infinity means then we can write dx comma dy comma dz comma 0. D comma 0 is nothing but the direction of the line. We can write this rewrite the inhomogeneous using r equal to p comma sorry p plus lambda into d bar. Okay. Then 3D quadratics. 3D quadratics similar to the 2D conics, we are having the same formula. X bar transpose into q into x equal to 0, which is used to represent 3D curved surface. Okay, 3D curved surface. Let us assume sphere. Let us consider a sphere with the radius r centered at the origin. This can be described as x square plus y square plus z square minus r square equal to 0. Or we can write x square plus y square plus z square equal to r square. Both are same. That is nothing but the sphere with radius r. Radius can be anything centered at origin. Since it is origin, we are representing is the 0, right? So the equation is x bar transpose q x bar equal to 0. Okay, so we know x bar equal to x, y, z and 1. Okay, x bar means homogeneous. We can represent 4 parameters since it is 3D. So in matrix, we can write x, y, z transpose, and the q matrix here is 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 0 minus r square, which represents the radius of the sphere. Let us substitute in the equation x bar transpose q into x bar equal to x y z 1, the transpose of x bar, and 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 minus r square, and x is nothing but x y z 1. Okay, we have to perform the same matrix operations. So this is 4 cross 4, this is 4 cross 1, so we'll get a 4 cross 1 final 4 cross 1 matrix, and this is 1 cross 4. On performing matrix multiplication, we'll get a final equation x square plus y square plus z square minus r square equal to 0, which is nothing but the same equation. Okay, so if this point is not right means we can't perform any operation. So in order to represent the 2D in 3D, we can use the equation x bar transpose q into x bar equal to 0. Thank you.